Hello there, Mr. Sutton here, bringing you the BC Calculus 8-6 Part 1 Homework Solutions on Polar Functions Advanced Area. On this problem, we want to find the area enclosed by r equals 2 sine of theta. So let's start by graphing this out because this was a calculator question. So here I am on my calculator in polar mode, so I've got r equals 2 sine of theta. And I set my window to be from 0 to 2 pi, and I'm going by pi over 36s, just so I make sure it doesn't get choppy when I graph this. Let me zoom 0 this thing, and here is my graph. Okay, so it's a circle essentially. So we want to find the area of this circle. Now, one way to do this would just be by using geometry. I mean, we have a radius of 1, so pi r squared would work pretty well. But if you want to use an integral, we've got our area formula, integral from a to b, 1/2 r squared d theta. So here we need to pick the limits of integration and the r value. Well, the r value is pretty easy. They gave it to us right here, so we'll just put that in there. So 1/2 times that stuff squared. And now we need our limits of integration. Now, before we go ahead and pick a 0 to 2 pi, which is often the limit of integration, let's go back to the calculator, since we're allowed to use it, and let's use the trace function on here and see how far it actually takes us angle-wise to get all the way around this circle that we're trying to find the area of. So I'm starting at the pole, 0, 0, and as I press, right here to go through my angles, I'm halfway around when I get to, well, this is really, you might recognize this as pi over 2. And then to get all the way around back to the pole, let's see, it's going to take me, well, actually just pi, not 2 pi. If I go to 2 pi, then I end up going all the way around the circle one more time. So if I just want the area of one circle instead of 2 circles, I need to use 0 to pi as my limits of integration. And now let me use the calculator for that. So here's what this looks like when I plug things in. My Math 9 integral from 0 to pi, we've got 1/2. I stored this as r1, so I can just do alpha trace r1 squared, and I have a d theta. All that coming out to about 3.1416, or just, I guess, 2, you could round it off, basically pi, when all is said and done. For this problem, we want to figure out an expression for the area inside the polar curve r equals 4 sine of theta and outside the curve r equals 2. This is a calculator problem, at least in terms of graphing it. I mean, it's a setup only, but we can use the grapher to at least see what we're looking at. So let's go ahead and do that. So here are my two curves entered in the r equals in polar mode for my calculator. And let me zoom fit these things. Zoom 0. I've got a window from 0 to 2 pi. So we've got a circle above the x-axis and a circle centered on the origin. And we want the area inside the top circle here, but outside this center circle. So this area right in here. So let me just draw a little quick picture there. So how do we get this area? Well, there's a few ways of doing this, but I'm just going to use some integral areas. So in general, my area formula is integral from a to b of 1/2 r squared d theta, but I'm going to have to split this up into two integrals. I basically want to find the area of this top circle from this spot right here to this other spot, and then I want to subtract the area of this bottom inner circle, again, from this spot to this spot. I want to use these spots here because if I go further down and just find the area of this whole circle, then I'm getting some extra stuff in here that my subtracting the radius of my inner circle is not getting rid of. So I need to find these intersection points, whatever I'm going to do else on this problem. And I could find these intersection problems on the calculator, these intersection points, but if you look at the limits of integration here, I mean, these things are expressed in terms of pi, so probably just setting these two curves equal to each other and solving algebraically is going to get me the exact values a little faster than trying to figure out what the decimals on my calculator are equivalent to. So setting these equal, we can divide by 4, so that's 1/2 that sine equals. And where does sine of theta equal 1/2? Well, that happens at 30 degrees, and using reference angles 150 degrees, and you could keep going around the circle, but it looks like those are the big two spots that we see there. So we'll call that pi over 6, and 5 pi over 6. So those are going to be our limits of integration. We want to integrate from here all the way to here. Okay, well, in order to do that, I'm going to start with an integral from pi over 6 to 5 pi over 6 of, so now I want the top circle here. That's this 4 sine of theta. So we're going to take half of that and square it. And then I need to subtract an integral on the same interval of this inner circle. So 1/2 times 2 squared d theta. Now this doesn't match any of the answer choices, so we are going to have to simplify this a little bit. So what do we need to do in order to simplify this? Well, one thing I notice, there's different orders you can do things in. One thing I notice is I have the same limits of integration here, and all the answer choices have just a single integral with, interestingly enough, something minus something else. So I'm going to move these integrands together into one big integral. And actually, since these both have a 1/2 inside here that I could pull out as a multiplier, I'm going to factor 1/2 out of all of this stuff. So I'm going to have 1/2 times a big integral from pi over 6 to 5 pi over 6. Now what's left inside? Just the stuff that was left inside with these original integrals. So 4 sine of theta squared and 2 squared. So I've got those two things then being subtracted inside one big integral. And just to simplify this a little bit more, this is going to be 16 sine squared of theta minus 4, which is going to end up giving me, let's see here, is it choice? No, it's not choice E. We need a pi over 6 to 5 pi over 6. So choice D, does that match everywhere? It does, so choice D. On this problem, they want the total area between these two polar curves. This is a calculator problem, so I'm immediately going to put these in my y equals, or r equals, I guess, for polar mode, and graph this out. And actually, I said immediately, but before I even do that, I don't feel like rewriting these every single time I want to use them, so I'm going to name them. This first one I'm going to name r sub a of theta, and this other one I'll call r sub b. All right, so let's graph out a and b. So here we are in my r equals, because again, I'm in polar mode for my calculator. I've got my window set to 0 to 2 pi. Integrals or intervals of, or step intervals of pi over 36. So here's everything I've got in window. Pi to 2 pi. This is actually pi over 36 here. Zoom fit, zoom 0. Let's see what all this is going to look like. So we've got two curves. We've got one petal, one rose, and here's another rose. So this first one is the smaller rose. This other one's our bigger rose. We want the area between the roses, essentially. So inside the big rose, but outside the small rose. So essentially, we just need to subtract the small rose from the big rose. Before we go ahead and do that, though, let's use the trace function on the calculator just to see what kind of intervals I'm going to need to get all the area for these. So let me do trace, and we'll start with the small rose, just moving along here. So there we go. There's our little spider going around in kind of an intuitive fashion, but then it dips down here, does that bottom petal, and it's going to come all the way back through here. And by the time we make it back to the pole, we've gone an angular distance of pi. Okay, well that's good to know, because if we went 2 pi, we would go all the way around again. And we don't want to do that. We just want to go around once to get all the area from radius strips. Let me do down arrow, and you'll see that my function that I'm on has changed, but I'm back at pi there. So let me just do 0 and start there again. So now tracing around from 0 onwards, we're going around the big rows now, and we take pretty much the same path just along a larger radius. And it takes us a distance of pi radians to get all the way around that one as well. So in general, both functions, we sweep out all the area on the interval from 0 to pi. So when I use my area formula, those are going to be my limits of integration. Again, if you go 0 to 2 pi, you're double counting all the area, which probably is not going to give you the answer you wanted. All right, so our general strategy then, subtract the small petals from the big petals on this interval. So I've got the interval from 0 to pi of the big radius here. So this is going to be 1/2 times rb squared d theta. And then I'm going to be subtracting the integral along the same length there. So from 0 to pi of 1/2 RA squared. Now, you could do two integrals on your calculator, and it's not a huge deal. But if you're really lazy and want to do less work on the calculator, you could simplify this a little bit. I can take a 1/2 out of both of these and move things into one big integral. So I can write 1/2 integral from 0 to pi, and then just RB squared minus RA squared d theta. That also works, and that should be an RA right there. There we go. And now let's go ahead and do that on the calculator. So here's what that looks like on my calculator, and I've got an extra 2 in there. There we go. So I've got 1/2 integral from 0 to pi, and then RB I stored as R2, so we square that and subtract R1 squared d theta. All of this giving us a final answer of about 30.631, which is going to be good for choice C. For this problem, we want an expression that gives us the total area enclosed by r equals sine squared of theta, shown here in the graph. So my general strategy on this one, since these are both exactly the same area it looks like, is I'm going to find the area of this top balloon-shaped sort of thing, and then I'm just multiply that by 2. So find the area of one oval, multiply by 2. So to get the area of one oval, we need to figure out our limits of integration. I mean, r is r, but limits of integration. So let me figure out where sine squared of theta equals 0, where we're basically going through the pole. We can start by square rooting both sides, so we have sine of theta equals just 0. And sine of theta equals 0, the y value on the unit circle is 0 at the values of 0 for theta and also for pi, and you could just keep going around, but those are the first two. So does going from 0 to pi give us this top oval, in case you're wondering? Well, if you were to plug in something in between like pi over 2, sine of pi over 2 would be just 1, and squaring that gives us 1. So yes, we would get this top circle. So then the integral from 0 to pi of 1/2 r squared is going to give us the area of the top here. If we want the overall area, we need 2 times the integral from 0 to pi of 1/2 sine squared theta d theta. But that doesn't match any of the answer choices, not exactly. So a couple things we can do. One thing is the 2 and the 1/2 can get multiplied to cancel out. And then this sine squared, if we actually square that, that's sine to the 4th power of theta inside there. So 0 to pi then, just 1 0 to pi. And then sine to the 4th, that's going to give us choice D. On this free response problem, where we can use a calculator, we've got this crazy looking collection of shapes here. Apparently these are the graphs of the polar curve r equals 3, which is the circle here with a radius of 3, and 3 minus 2 sine of 2 theta, which is this other weird, lumpy, kind of half a Mickey Mouse sort of shape. And we're on the interval from 0 to pi. So, first part, if we have r as this shaded region, we want to find the area of that. Well, for this, there's a few ways to do this one. But at the end of the day, if I want to find the area of the shaded region, probably the easiest way to do this, I mean, this quarter circle here, I can just use basic geometry to get this quadrant 2 part of the circle. And we don't want anything that's out here anyway. But this part, I am going to need an integral. I'm going to need to subtract some things with these two functions. So to do that efficiently, so that I don't have to keep rewriting this expression over and over again, I'm going to rename this r to f of x, or actually f of theta. Let me use f of theta here. So now that I've renamed this here, to get my area of the shaded region of r, I've got a quarter circle, so 1/4 pi r squared. We have an r value of 3, so 1/4 times pi times 3 squared. And we'll let the calculator figure all of this out when all is said and done. And to that, I'm adding this area over here now. This is going to be, let's see, we basically just have the area inside the f of theta curve here between 0 and pi over 2 radians. So integral, adding integral from 0 to pi over 2 of 1/2 times f of theta squared d theta. Let me put all that now in my calculator. So to start, I've actually entered both polar functions in my calculator, And if I want to zoom zero this thing, I can graph it out so I can get my own version of this on the calculator. There's my circle, and there apparently is the rest of the shape they're not showing us. Looks like we're not missing much happiness there. So now, quitting out of that, I have, let's see, 1/4 pi times 3 squared. And now I have to add an integral. So plus, let's see, we got math 9, integral from 0 to pi over 2. And inside we've got Francie fraction 1/2. And now we've also got the f function here, which I stored in R2. So I'm going to do alpha trace, and that brings up my R menu, my y-vars menu. That's R2. Square that. Stick a theta in there. Press enter. And we have a grand total of about 9.708 if we round off. For this next part, for the curve 3 minus 2 sine of 2 theta, which again we've renamed this as f of theta, we want the value of dx over d theta at x equals pi over 6. All right, so in order to get this, we have to express this parametrically with an x. In general, we can say that x of theta equals x, or rather r, times the cosine of theta. In particular, the r value that we care about here is represented by the f of theta function that we renamed this thing to be. So this is a function for x of theta. Now, if I want to find dx over d theta at theta equals pi over 6, I basically just now need x prime of theta for this function at pi over 6. I could figure out what this thing looks like in terms of a formula, but I don't really need it yet. So on my calculator, I'm allowed to take the derivative of a function that I've defined at a specific spot. Since I've already told you what f of theta equals, and we know what cosine of theta equals, writing this out fully defines the x of theta formula. So I can now just plug this into my calculator and take the derivative at pi over 6. Let's go ahead and do that. So here we go. For this, I'm going to do math 8 n deriv, and we'll do, I'm already in polar mode, so it does d theta down there. Up here, I've got, let's see, this was stored as R2 in my calculator, so alpha trace R2. And I'm multiplying that times, I'll just put a times in here to make sure I'm not plugging something into this, multiplying that by cosine of theta. And I want to evaluate all that craziness at pi over 6. So pi divided by 6 equals, and this is going to be negative 2.366. For this problem part, they're telling us the distance between the two curves changes from 0 to pi over 2. So right from here to here. I mean, it changes in the other spot too, but this is the only part they care about. Find the rate at which the distance between the two curves is changing with respect to theta when theta equals pi over 3. So the good news is that the distance between the two curves is actually like if you took the distance from the origin to each curve and subtracted those, that would give you the distance between the two curves, because they're both kind of lined up at the same angles as we go with respect to the origin. So I'm going to start by writing a function that gives me the distance between the two curves, and then I'll figure out the rate at which it's changing at pi over 3. So I'm going to call this d, big D of theta. And the distance between the two curves, again, since these r's are both just telling us the distance from the origin, it's just going to be the outer curve minus the inner curve. So this is going to be 3 minus, and I called this f of theta. So this is the thing I'm taking the derivative of. Since I already told you what f of theta is in part A, this is a fully defined function. And since I just want the derivative at a specific spot, namely pi over 3, I'm just going to do d prime of pi over 3 and plug this in the calculator. So here's what that plug-in looks like on my calculator. I'm taking derivative of 3 minus R2, that's where I stored f of theta, doing that at theta, or pi over 3 rather. Press enter, and that looks to be approximately negative 2.0. It's probably negative 2. I'll just write this though, and that's accurate to 3 decimals, so we're good. For this problem, we have a particle going along this curve so that d theta over dt is 3 at all times. We want to find the value of dr over dt at theta equals pi over 6. So let's see here. We've got one rate of change. We want another rate of change at a specific input value. This is a related rates problem. Here's the equation that ties everything together, because they're just talking about thetas and r's. There's no x's or y's messing things up. So we can just start with this and imp diff this thing, and then plug in what we need to. So derivative, now this is all going to be with respect to time. So any letter that's not t is treated as an inner function. So the derivative of r, for example, that's going to be dr over dt. And then let's see, 3 gets differentiated away to 0 for negative 2 sine of 2 theta. This is going to be, using the chain rule, negative 4 cosine of 2 theta. Now we have to multiply by the inner derivative of this function here. So we actually already took care of the 2, but the theta we haven't taken care of. That's going to be d theta over dt. And now it's time to see what we can plug in. So we ultimately wanted to know the value of dr over dt. We've already got it isolated. We just need to plug in things for theta, which they said was pi over 6, and for d theta over dt, which they spelled that out as well. They said that was 3. And we could actually leave it like this and call it a day, because these are all considered constants. But if you needed to simplify it just to feel happy, this is really cosine of pi over 3, cosine of 60, which is 1/2. Negative 4 times 1/2 is negative 2. Multiply that by 3, we've got negative 6.